C# and AI Masterclass by Edgar Milvis Volume 9, Chapter 15. Moving on to Chapter 15, Whisper.net, Local Audio Transcription. Let's discuss theoretical foundations. The theoretical foundation of local audio transcription with Whisper.net rests on the convergence of three distinct domains: the architectural principles of transformer-based sequence-to-sequence models, the computational efficiency of the ONNX, Open Neural Network Exchange, runtime, and the memory management capabilities of the .NET runtime. To understand how we achieve real-time, edge-based transcription in C#, we must dissect the Whisper architecture and map its requirements to the specific abstractions provided by the .NET ecosystem. Now, let's talk about the Whisper architecture, from audio to token sequences. At its core, the Whisper model is not merely a speech recognition engine, it is a multitask, multilingual model trained on approximately 680,000 hours of audio data. Unlike traditional automatic speech recognition (ASR) systems that rely on hidden Markov models, HM, or connectionist temporal classification (CTC), Whisper utilizes a transformer-based encoder-decoder architecture. The encoder, audio representation. The input to the system is not raw PCM audio samples, which are high-frequency and noisy. Instead, the audio undergoes a critical pre-processing step known as the short-time Fourier transform (STFT). This converts the raw audio signal into a log-mel spectrogram, a visual representation of the spectrum of frequencies of the signal as they vary with time. Imagine looking at a piano roll in music production software. The horizontal axis represents time, and the vertical axis represents pitch, frequency. The intensity of the color represents the loudness at that specific pitch at that specific moment. This 2D image-like representation is what the Whisper encoder processes. The encoder is a standard transformer encoder stack, specifically based on the Vision transformer architecture, adapted for audio. It does not hear the audio, it sees the spectrogram patterns and extracts high-level semantic features from them. The decoder, token generation. The decoder is an autoregressive transformer decoder. It takes the features extracted by the encoder and generates a sequence of tokens. These tokens represent text characters, but also special task tokens, e.g., transcribe, translate, and timestamp tokens, to synchronize text with audio time. This is where the sequence-to-sequence, seek-to-seek, paradigm becomes vital. The model maps a variable-length input sequence, audio frames, to a variable-length output sequence, text tokens. The critical theoretical concept here is attention, specifically the self-attention mechanism. The model learns to attend to relevant parts of the audio spectrogram when generating a specific word. For instance, when generating the word hello, the decoder attends to the high-frequency components of the spectrogram corresponding to the H sound, effectively focusing on the relevant region of the input data. Let's discuss the ONNX runtime, bridging frameworks to hardware. While the model architecture is defined in PyTorch or TensorFlow, running it efficiently in a C# environment requires a standardized interchange format. This is where ONNX plays a pivotal role. ONNX is an open-source format for representing machine learning models. It decouples the model definition from the hardware execution. When a Whisper model, originally trained in PyTorch, is exported to ONNX, it is converted into a computational graph, a directed acyclic graph, DAG, of operators, add, matmul, layer norm, etc. Why ONNX is critical for Edge AI? In the context of Edge AI, hardware heterogeneity is the primary challenge. A C# application might run on an x64 Windows desktop with an NVIDIA GPU, an ARM-based Raspberry Pi, or an Android device. Writing native code for each hardware target is infeasible. ONNX runtime (ORT) acts as a highly optimized execution engine. It parses the ONNX graph and applies graph optimizations, like operator fusion, constant folding, and layout optimization, specific to the available hardware. For example, on a CPU, ORT might fuse a layer norm and an add operation into a single kernel to reduce memory bandwidth. On a GPU, it might leverage CUDA or DirectML kernels for parallel execution. In C#, the Microsoft.ml.onx runtime NuGet package provides the managed wrapper. It abstracts the underlying C++ execution provider. This allows the developer to write a single C# codebase that dynamically switches execution providers, CPU, CUDA, TensorRT, OpenVINO, based on the deployment environment, ensuring maximum performance without recompiling the application. Now, let's talk about the C# ecosystem, memory management and asynchrony. Transcribing audio locally presents significant computational and memory challenges. A 60-minute audio file processed by Whisper generates a massive spectrogram tensor, which is then fed into a model that may have billions of parameters, e.g., Whisper large. The role of idisposable and span T in a managed language like C#, the garbage collector, GC, is responsible for memory management. However, in high-throughput AI pipelines, unmanaged memory allocated outside the GC heap, typically used by the ONNX runtime for tensor data, must be handled precisely. If not managed correctly, memory leaks will occur, crashing the application on resource-constrained edge devices. The idisposable pattern is the standard mechanism in .NET for releasing unmanaged resources. In Whisper.NET, objects representing the ONNX session, the audio stream, and the inference tensors implement idisposable. The theoretical imperative is to ensure that the lifecycle of these unmanaged resources is strictly tied to a using statement or a try-finally block. This mimics the RA, resource acquisition is initialization, pattern found in C++, ensuring that memory is released deterministically the moment the transcription of a segment is complete. Furthermore, modern C# utilizes span T and memory T to handle buffer pooling. When reading raw audio bytes or processing the spectrogram array, span T allows us to work with slices of memory without allocating new objects on the heap. This is crucial for real-time transcription, as it prevents GC pauses that would cause audio glitches or latency spikes. Asynchronous pipelines, real-time transcription requires the application to capture audio input, microphone, and process it concurrently. In C#, the async/await pattern is the architectural backbone of this concurrency. The theoretical model here is a producer-consumer queue. 1. Producer, an audio capture loop runs on a separate thread, filling a buffer with PCM samples. 2. Consumer, the Whisper inference engine runs asynchronously, taking filled buffers, converting them to tensors, and performing inference. By using task T and value task T, we offload the heavy matrix multiplication operations to the thread pool, preventing the UI thread, or the main application loop, from blocking. This is essential for edge AI applications where the user expects immediate feedback. Now, let's talk about analogy, the multilingual librarian. To visualize the entire process, imagine a highly specialized librarian, the Whisper model, working in a soundproof room, the edge device. 1. Input, the spectrogram. You hand the librarian a continuous strip of ticker tape, the audio spectrogram. The tape has holes punched in it representing frequencies and intensities. The librarian does not read the tape like a text, they look at the shape of the holes, the visual pattern. 2. The encoder, the cataloger. The librarian takes the ticker tape to a cataloging desk, the encoder. They analyze the patterns and write down abstract concepts on index cards. For example, instead of high-pitch spike, they write sound of a flute. 3. The decoder, the translator. The librarian takes these index cards to a writing desk, the decoder. Based on the cards and the context of previous cards, attention, they start writing words on a piece of paper. 4. The execution engine, the librarian's assistant. The assistant, ONNX runtime, organizes the index cards and writing tools on the desk in the most efficient order possible, so the librarian doesn't have to waste time searching for them. 5. The C# application, the librarian's manager. The manager, C# code, ensures the librarian has a steady stream of ticker tape, audio capture, and that the written pages, transcription results, are filed away immediately without piling up, memory management. Let's discuss architectural flow visualization. The following diagram illustrates the data flow from raw audio to transcribed text, highlighting the separation between managed C# code and unmanaged ONNX execution. Diagram, architecture. Moving on to deep dive, the inference pipeline mechanics. To understand the how of local transcription, we must look at the specific tensor manipulations occurring within the ONNX session. 1. Audio preprocessing, the MEL filter bank. Before the data ever reaches the ONNX model, the C# application must perform the same preprocessing used during training. This is not optional, a mismatch in input representation will result in garbage output. The raw audio, usually 16 kHz, 16-bit signed integers, is converted to floating point values between -1.0 and 1.0. A MEL filter bank is applied to the spectrogram. This mimics human auditory perception, where we are more sensitive to differences in lower frequencies than higher ones. Why this matters in C#, this operation is computationally expensive. While ONNX can handle some preprocessing, doing it in C# using optimized libraries, or SIMD via system, numerics, allows us to prepare the tensor buffer before inference, reducing latency. 2. The encoder pass. Once the MEL spectrogram tensor is ready, shape, batch_size, 80, 3000, for a 30-second chunk, it is passed to the encoder. In the ONNX graph, this involves multiple layers of multi-head attention and feed-forward networks. Theoretical note, the encoder outputs a hidden state vector, context vector, for every time step. This vector encapsulates the semantic meaning of the audio at that moment. 3. The decoder pass, autoregression. The decoder generates tokens one by one. It starts with a special, start of transcript, token. Step A, the decoder takes the encoder's output and the previously generated tokens, if any, and predicts the next token. Step B, the predicted token is fed back into the decoder as input for the next step. Step C, this continues until an end of transcript token is generated. C# implementation, this loop must be implemented carefully. In a naive implementation, this would block the thread. In an advanced C# implementation, we use IEnumerable or IAsync enumerable to yield tokens as they are generated, allowing the UI to update incrementally. 4. Timestamp prediction. Whisper is unique because it predicts timestamps alongside text. It uses special tokens like 0.00 to mark the start and end of a segment. This requires the model to align the audio representation with the text generation. Theoretical implication, the model is not just mapping audio-text, it is mapping audio-text plus time. This requires the decoder to attend to the positional embeddings of the encoder output, the time dimension of the spectrogram. Let's discuss edge AI considerations and optimization. When deploying this in a C# application on the edge, several theoretical constraints must be managed. 1. Quantization. Standard Whisper models use 32-bit floating point numbers, FP32. This provides high precision but consumes significant memory and bandwidth. For edge devices, especially mobile or IoT, we often use quantization. This converts the model weights to 16-bit floats, FP16, or 8-bit integers, INT8. Impact. Quantization reduces model size by 2x, 4x and speeds up inference on hardware that supports integer math, like NPUs. ONNX runtime handles this transparently if the model is quantized correctly. In C#, we simply load the quantized ONNX file, the code remains identical. 2. Beam search versus greedy decoding. Greedy decoding, at every step, pick the token with the highest probability. It's fast but can miss the best overall sentence. Beam search keeps track of the top $k, beam width, most probable sequences. It's more accurate but computationally heavier. C# strategy. For real-time transcription on low-power devices, greedy decoding is often preferred for speed. However, for offline transcription of critical files, beam search, implemented via ONNX runtime's generation parameters, is superior. The choice depends on the latency versus accuracy trade-off specific to the application. 3. Streaming versus chunking. Whisper was trained on 30-second chunks. To transcribe a 1-hour meeting, you cannot feed the whole hour into the model at once, memory constraints. Sliding window, the audio is sliced into 30-second segments with a stride, overlap. The overlap ensures that a word split between two segments is captured fully in at least one. Context carryover. In a sophisticated C# implementation, the final hidden state of the previous chunk can sometimes be used to initialize the next chunk, maintaining context. However, standard Whisper treats chunks independently. The C# application must stitch the results together, removing duplicate words at the boundaries. Moving on to integration with previous concepts, the ONNX session. Referencing the foundational concepts established in Book 8, ONNX Runtime Integration, the Inference session class is the central object. However, in the context of Whisper, we utilize advanced features of this session. Specifically, we utilize session options to configure the execution provider. In a previous chapter, we discussed how to load a model. Here, we must consider the specific memory requirements of the Whisper model. Whisper Large v3 has approximately 1.55 billion parameters. In FP32, this requires roughly 6 GB of VRAM or RAM just for the weights, plus activation memory. The inference session constructor in C# allows us to pass execution mode .ort_sequential, default, or ort_parallel. For audio transcription, sequential is usually sufficient as the graph is a linear pipeline, but for multi-streaming, transcribing multiple audio sources simultaneously, parallel execution becomes relevant. Now, let's talk about the role of interfaces in abstraction. As emphasized in previous chapters regarding model swapping, the theoretical design of a transcription system should rely on interfaces. While this subsection is theoretical, the architecture implies the following. Here, we're defining a C# interface named iAudioTranscriber. This is a crucial architectural decision. By using an interface, we are establishing a contract for any class that wants to provide audio transcription services. This promotes loose coupling, meaning our application's core logic doesn't depend on a specific transcription implementation. For example, we could easily swap out a Whisper-based transcriber for a Google Cloud speech-to-text transcriber, or even a future, more advanced local model, without altering the consuming code. The transcribe async method is the heart of this contract, taking an audio stream and a cancellation token, and returning a transcription result asynchronously. This asynchronous pattern is vital for non-blocking I/O operations, especially when dealing with potentially long-running tasks like audio processing, ensuring our application remains responsive. Now, let's look at a concrete implementation signature, Whisper Transcriber. This class explicitly states that it implements iAudio Transcriber, thereby promising to fulfill the contract defined by the interface. It also implements iDisposable, which is a strong indicator that this class manages unmanaged resources or resources that need explicit cleanup. In this context, it's highly probable that the inference session and session options, which we'll discuss next, are such resources. The _session field, of type inference session, reveals that this transcriber relies on ONNX runtime for its inference capabilities. This is where the heavy lifting of running the Whisper model will happen. The _options field, a session options object, allows us to configure how the ONNX runtime session behaves, including specifying execution providers, CPU, GPU, etc., and other performance-related settings. This separation of concerns, the interface defining what to do, and the class defining how to do it with specific tools, is fundamental to building maintainable and scalable systems. This abstraction is vital. If a more efficient native library for Whisper emerges, e.g., a Rust-based backend, we can implement iAudio Transcriber without changing the consuming C# application logic. This adheres to the dependency inversion principle, a cornerstone of robust software engineering. Turning our attention to theoretical foundations. The ability to run Whisper locally in C# is not magic, it is the orchestration of complex mathematical operations managed by a robust runtime environment. 1. Mathematical foundation, the transformer architecture, encoder-decoder, utilizing self-attention to map spectrograms, time-frequency representations, to token sequences. 2. Computational foundation, the ONNX runtime providing a hardware-agnostic execution engine that optimizes the computational graph for specific edge devices. 3. Software engineering foundation, the .NET runtime providing memory safety, iDisposable, GC, concurrency, async/await, and buffer efficiency, span-T, to handle high-throughput data streams without resource exhaustion. By mastering these theoretical underpinnings, the developer moves from simply calling an API to architecting a self-contained, efficient, and private AI system capable of running on any edge device supported by .NET. Let's discuss basic code example. The problem: local audio transcription for a smart meeting assistant. Imagine you're building a smart meeting assistant that runs entirely on a user's laptop. This assistant needs to transcribe audio from a meeting recording in real time, without sending sensitive corporate data to a cloud service like Google Speech-to-Text or AWS Transcribe. You need a solution that is fast, private, and works offline. This is where Whisper.net comes in, allowing you to run OpenAI's powerful Whisper models locally using the ONNX runtime directly within your C# application. Here is a simple Hello World example that transcribes a WAV audio file into text using Whisper.net. Here, we're importing essential namespaces that provide functionalities needed for our application. Notice system.io for file operations, like reading our audio file, and system, threading, tasks for asynchronous programming, which is crucial for non-blocking I/O operations and efficient resource utilization, especially with potentially long-running tasks like audio processing. The Whisper.net and Whisper.net GGML namespaces bring in the core libraries for interacting with the Whisper speech-to-text model, specifically the GGML, Georgy Jurganov's machine learning, backend, which is optimized for CPU inference. This choice implies we're prioritizing local, CPU-based execution over GPU or cloud inference, making it suitable for edge AI scenarios. We define our application's namespace Whisper Local Demo to organize our code and prevent naming conflicts. Inside, the program class acts as the entry point for our console application. The main method, declared as static async task main, string, args, is where execution begins. The async task return type is critical here. It signals that this method performs asynchronous operations, allowing the program to remain responsive while waiting for I/O bound tasks, like file reading or model processing, to complete. Without async, these operations would block the main thread, leading to an unresponsive application, especially in a UI context. At line 16, we define audio file path as sample.wav. This is a hard-coded path for simplicity in this Hello World example. In a production application, this path would likely be dynamic, perhaps obtained from user input, a configuration file, or a real-time audio stream. The if file exists audio file path block from lines 19 to 24 is a vital defensive programming practice. It checks for the existence of the audio file before attempting to process it. Failing to do this could lead to a file not found exception at runtime, crashing the application. Providing a clear error message to the user, as seen at lines 21 to 22, significantly improves the user experience and debuggability. After confirming the audio file's presence, we print a confirmation message at line 26, which is good for user feedback in a console application. Then, we define model path at line 31 as ggml_tiny.bin. This specifies the particular Whisper model variant we intend to use. The tiny model is chosen here because it's lightweight and fast, making it ideal for quick demonstrations and environments with limited computational resources. While not as accurate as larger models, its small footprint and speed are perfect for an introductory example. The Whisper.net library is designed to automatically download this model if it's not already present locally, simplifying setup for the user. Look at lines 33 to 37. We initialize the Whisper factory using whisperFactory.FromPath, model path. This factory is the central component for managing the Whisper model. It abstracts away the complexities of loading the ggml model file, handling its internal structure, and preparing it for inference. The using statement here is crucial. It ensures that Whisper factory and its underlying resources, like model handles or memory allocations, are properly disposed of once they go out of scope. This is a best practice for resource management in C#, preventing memory leaks and ensuring efficient cleanup. At lines 38 to 47, we begin building the Whisper processor. We obtain a builder from our Whisper factory and then chain configuration methods. With language, N, is a key optimization. Explicitly telling Whisper that the audio is in English significantly improves both accuracy and transcription speed. Without this hint, the model would spend time trying to detect the language, which adds overhead and can sometimes lead to misinterpretations. This is an example of providing domain-specific knowledge to improve model performance, a common practice in machine learning applications. The with-segment event handler at lines 45 to 50 is a powerful feature for real-time or streaming transcription. Instead of waiting for the entire audio file to be processed, this callback fires whenever Whisper successfully transcribes a segment of speech. A segment usually corresponds to a sentence or a coherent phrase. This allows for incremental display of results, which is vital for user experience in live transcription applications. The callback provides segment, start, segment, end, timestamps, and segment, text, enabling us to present the transcribed text with timing information, much like subtitles. Finally, at line 53, we call build on our processor configuration to create the actual Whisper processor instance. Again, we use a using statement for processor to ensure proper resource disposal. Then, at lines 55 to 58, we open the audio file using file.openRead, audio file path. This creates a file stream that allows us to read the audio data. Whisper.net expects the audio in a specific format, typically 16-bit PCM, 16 kHz sample rate, mono channel. While the library handles internal buffering, ensuring the input audio adheres to these standards is crucial for correct transcription. If the audio is in a different format, pre-processing, e.g., using libraries like NAudio, would be necessary. The core transcription action happens at line 60 with await processor.processAsync file stream. This asynchronous method streams the audio data from our file stream to the Whisper model. The await keyword ensures that the program pauses execution at this point until the entire transcription process is complete, without blocking the main thread. As segments are processed, the with-segment event handler we configured earlier will be invoked. Once processAsync finishes, indicating all audio has been transcribed, we print transcription completed at line 62, providing a clear end-of-process indicator to the user. By scanning this code you can go to the website with more details and with buying options. On leanpub.com you can find the discounted bundle with all the volumes. This lesson is excerpted from Volume 9, Chapter 15 of the C# and AI Masterclass ebook series and from the volume Edge AI and Local Inference. Running LLMs, Llama/Phi, locally with C# and ONNX. You can find all source code here, https://github.com/edgarmilvas/C# programming series. The ebook includes 20 chapters, each one with diagrams, advanced examples, and 5 exercises with solutions. Subscribe to the channel to watch more videos. Thank you for your attention. I look forward to seeing you in the next lesson.